Welcome everyone. Sorry that we're getting going on Maui Standard Time, which is about 5 minutes late from when it's supposed to be. It's a great pleasure today to be here. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist at the University of Hawaii Institute for Astronomy. And one of the things I get to do for part of my job is to put together talks like this one. And we have Dan O'Gara, who's been with the Institute for Astronomy for a number of years. He's the superintendent of the Haleakalā Observatories. He's also the PI for the NASA Laser Ranging Station up at the summit of Haleakalā. And he got his degree at the University of California at Irvine. He's a bachelor's degree in mathematics. So everyone paying attention, you know how important math is, right? He spent about 7 years as a software engineer, and then he came out here to work for the laser ranging, and he was one of the guys on the original LURE station that measured the distance to the moon. Correct? All right. So this is one of the experts in laser ranging. Let's give him a nice Maui welcome.
I don't give many talks, so.
So, is the loop comfortable?
I guess so. Just hardly feel it. Yeah.
And that's yes.
Okay.
Okay. And then try talking.
Hello, can you hear me?
Is that good?
Okay. Oh, there's a delay.
Yeah, there is a delay.
Okay.
That's a good level today.
Hello?
Okay.
1, 2, 3. 1, 2, 3. Okay.
Okay.
Oh, okay. Well, thank you all for coming. As I mentioned, I don't give talks very often, so if I'm a little rough, excuse me. I am not a doctor. I'm an engineer, and I was hired in 1984 to get this system to actually get its first measurements to the moon. The LURE Observatory was established in '72 to do that, and they weren't. Thank you. They weren't successful, and in 1984 we got new technology with lasers, and NASA put some more money in, and we actually were successful. So I'm going to start off just giving a brief explanation of what laser ranging is. It's just making distance measurements between an observatory and a satellite, and I put artificial or natural in there because the moon is just another satellite, and it can be made by measuring the time of flight of short pulses of laser light. So all we do is we fire a laser, and the laser hits the target, hopefully, and when it's reflected back, we stop the timer, and we have the distance because we know the speed of light. And that's all there is to it. So, however, it took us 13 years to get ranges back from the moon. So it's a little more difficult than it sounds. Part of the course with the moon, of course, is because it's so far away. It was difficult to get the photons back because even though we're using a laser, it does spread out some, and by the time it gets back, we're only seeing a few photons. But besides lunar ranging, we also do satellite ranging. And why do we do this? And the reason is geodesy. I'm not an astronomer, and I'm not doing astronomy. We're doing studies of the Earth. When I first heard about this many years ago, when I was in high school, this Greek mathematician by the name of Eratosthenes in 240 BC calculated the circumference of the Earth. And he did it probably within about 2 or 3% error. And I found that so amazing that just using what he knew about the Earth, that in his small part of the world, which was Alexandria, he noticed that during the summer solstice, the wells at Cyrene, which was south of Alexandria, there would be no shadow because it was in the tropics. Actually, it's a little out of the tropics, but close enough that during the solstice, the sun was right overhead, and there'd be no shadow. But he noticed at his place up in Alexandria, there were shadows. And he set up, I don't know who he got to do it, but somehow he measured the distance between Cyrene and Alexandria, which was, it's quite a distance. Apparently he had someone just walk it off. And he measured at noon, he measured the angle here that was being caused by the sun, and based on real minor stuff, I looked this up, and they teach us now in 8th grade, that this angle is equal to this angle. And he knew the distance here, and the angle there was like 7 degrees, which is, let's see, 50 times, no, I'm sort of forgetting now. Oh, it was 7 degrees, which was 7.2 degrees, which is like 1/50th of 360, which is the full circle. So he just multiplied that distance, which he had 4,400 stadias by 50, and he came up with a number, which was within a few percentage points of the actual value. So anyway, that amazed me as a mathematician, sort of, and with geometry. It was just amazing he could do that from sitting in his library at Alexandria. So geodesy deals with this measuring everything about the Earth. That includes the orientation of the Earth in its orbit, the shape, what it looks like, how it's rotating, and how much gravity exerts on us. I'm not going to talk much about the last one, although it's very important. We maintain the reference frames. In order to measure stuff on the Earth, you need to have points that you can measure from, and those are reference frames. That's another thing, very important thing that we do with the data. Let's see if I can get this to work. So for laser ranging, one way of getting a reference point is orbits, especially satellites that are in high orbits. They're very stable. And this is the basic equation. For example, let's say this is Hawaii and this is a observatory in California. They can make these measurements to these satellites. The distance here, these blue lines, is equal to 1/2 times the speed of light times the change in time for the pulses to go out and back. Well, you've got 2 parts of a triangle, and guess what? You can figure out the distance between these 2 points to the accuracy that you can range to the satellite. And right now, we're ranging to millimeter levels. So we can determine the distance between sites that are 2,000 miles away within a few millimeters. Oh, that's not. Let me go back. As I mentioned, I'm an engineer, and I'm really interested in the software and the hardware. The primary piece of equipment we use is a laser. Everybody knows about lasers? Well, the acronym stands for Light Amplification by Stimulated Emission of Radiation. And as I was putting these slides together, I came across his name quite a bit, by the name of A. Einstein. He was the one that actually proposed this. He got the stimulated emission part is something that he discovered. And so he actually described how a laser could operate. Better? Okay. I think that was probably in the teens or something. It was quite a while. It wasn't until the 1960s that someone actually was able to create a laser. We need a telescope, and that's needed to transmit the laser pulse out and to see the reflection. We need a time measurement device. And as you know, in order for accuracy, you need to be able to measure time very, very accurately. So the device we use on the summit right now, it's really an old device, but it still can measure time intervals to 35 trillionths of a second. So you put that together with a laser, which I forgot to mention that the pulse that comes out of the laser is 150 picoseconds in duration. So it's a very short pulse. So those 2 things together are the primary reason we can measure to millimeter level. And plus you do thousands of, if you know statistics, you do thousands of measurements, and you increase your accuracy by so many more measurements. The other thing here is the detector, which uses the photoelectric effect. That actually, I'll mention Einstein again on that. These detectors we have are able to detect a few photons of light. It's amazing they can do that. So when we were doing lunar ranging, which we don't do anymore, but we had a detector that could see a single photon. And of course, you get a lot of noise too. But if you're actually getting returns off the reflectors, you can statistically look at all the noise and you'll see the actual data, even at a single photon level. And you need a reflector. The corner cube, I don't know if anyone's heard of corner cubes. They're these special mirrors that no matter which angle the light comes in, it comes back out right back the way it came in. So it's not like a flat mirror that'll bounce off. It comes right back at you. So put that all together and you can do laser ranging. Now, there's all kinds of different kinds of lasers, but this is fundamentally how they all operate. In our case, we use what is called a solid-state laser. And I brought some damaged lasing rods. These are the actual rods that we use at the summit. This one's cracked, but this is that right there. And as Einstein says, you just hit this with white light, and it causes, these are neodymium crystals doped with yttrium, aluminum, and garnet. Now, those molecules provide us with the best results when you hit it with white light. You end up coming up with a laser light, which is coherent and all in phase. So it's same color, it's one color, and it's like a point source. It's very bright. If anyone's seen a laser, this isn't a laser. Is this a laser? Let's see, is it working? I mean, this is a good example. You see how bright it is, and it doesn't diverge. It just goes straight. So of course, this system here that we have produces infrared light, which you can't see. And later on in our optical system, we have another nice little piece of optics that will convert this infrared into green, and the light that goes out is green. That's basically all laser is. It's really very simple. I'm surprised that someone didn't think about it before. Well, oh yeah, you're still not working? I didn't shave this morning. On our side, in our telescope, we have a detector that can see the reflected light. But as I said, it's just a few photons sometimes. And it uses something called the photoelectric effect, which again, this guy A. Einstein showed up. That's actually what he got his Nobel Prize for in 1921. So what it does is it enables you to amplify really low light. And the detector we have, it's actually state of the art right now, even the one we have up there right now. It multiplies the incoming photons by a factor of 10 million. So that's why we can see a single photon. We also have to be careful of not damaging the thing. Let's see. Oh, God. And this is how it works. We have something called a multi-channel plate. That's actually an image of one we have in our system. And in the face, there's all these little channels. And as Einstein predicted, when these electrons come in and hit this electrified channels, it knocks other electrons off, and those bounce off and hit the wall again. They just multiply, and by the end you get a nice big multiplication factor, which allows us to see such low levels of light. And corner cube reflectors, I'd mentioned we need those in order to, a flat mirror, of course, would be chaos, because you have to hit it directly flat on in order to hit it. So we have these corner cubes, and I actually have some after the talk if you want to see it. I have some of these corner cubes here that if you look at it, you can see your reflection of your eye, and it just comes right back at you. So that way it makes it easier to get returns off satellites that have these things on them. All the satellites we track, and also the moon, we wouldn't see anything unless we had reflectors up there. So, well, unless we had a really powerful laser maybe, but we may. So this is the whole system in operation. You can see here's the telescope broadcasting a pulse, starts a clock, and when the pulse comes back, stops the clock. That's the whole system. Geodesy, although the ranging of the moon and the satellites is basically the same thing, because the moon's just another satellite, it's been traditionally sort of broken into two pieces because lunar ranging was so much more difficult. And that's what I got involved in first. And there's some specific products or science that's done with this data that you can't do with satellites. First of all, there's 5 targets on the moon, 3 left by Apollo and 2 by the Soviets in 69 through 72, I believe, was when these were left. And they're just, I have pictures of them. You've probably seen some of these pictures before. That's actually Apollo 11, 14, and 15. And I believe this is a picture of the astronaut putting down Apollo 11. But they're just flat arrays with these corner cubes on them. And that's what you've got to hit. You know, even though by the time we fire a laser to the moon, even when it's as collimated and as intense as a laser, it still spreads out. I don't give you the wrong numbers now, but it's probably a kilometer almost. So not only you have to hit that within a kilometer, the energy is spread out. So that's why we're only seeing single photons sometimes coming back, because by the time it goes there and back, you've lost quite a bit of the energy. The Soviets also put 2 targets on the moon. They were rovers. They were actually the first ones to put rovers on. In 1969, Lunokhod 1 and Lunokhod 2 was put on a couple of years later. And I put Lunokhod 1 in red because I don't know if you've heard the story a couple of years ago. What happened was Lunokhod 1, within a few months after landing on the moon, they moved it, and all the laser stations on the planet, we couldn't find it. You know, we were searching for it, couldn't find it. And this was 1972. This was actually before my time even. So they just figured that when they moved it, it tipped over or something. Well, I think it was 2 years ago, the Lunar Reconnaissance Orbiter, you heard about that mission that took high-resolution pictures? They flew over the area, and with the photographs, they could actually see it with the photographs. So there's a new laser ranging station, lunar station in New Mexico. It has a big telescope, has like a 4-meter telescope. They found it within a few minutes after after they saw the picture. And apparently it's still reflecting, the guy who runs the station out there said he's getting stronger reflections off that than any other. So now they determine where this guy is within a few centimeters on the moon. But I don't know, there's nobody else here from, when I first got here, we spent days, well, nights actually, trying to find that guy with our, you know, we thought we knew where it was, and it was just amazing they finally got it. Well, the fundamental thing you can do with lunar laser ranging is measure the distance. And since they've started taking these measurements in 1969, I think the first ones, they've noticed that the moon is moving away from the Earth at about 3.8 centimeters per year. The other thing you can do with this data is determine the rotation of the Earth. And you've all heard of leap seconds, right? Well, the Earth is slowing down. And that's why they had these leap seconds to adjust the clocks to match physically what the Earth is doing. But the Earth is slowing by 1.7 milliseconds per day per century as of a few weeks ago. So you don't have to worry about it stopping anytime soon. But those were 2 things that came out of lunar ranging almost immediately. Although I believe astronomers knew that the moon was moving away, they had no idea what the speed was. The other thing you can do is other lunar studies is the lunar composition. There's, for years they thought it was solid. And by looking at all those 4 targets and seeing how it moves, it's sort of like, you know, you can tell the difference between a hard-boiled egg and a soft-boiled egg, or a raw egg by spinning it. Well, they're able to do that with this, and they've determined that the center is partially molten. However, just last week I read another paper, somebody disputed it, you know. But based on what they, I think it does have a partially molten center, but they can tell it just by seeing how it rotates. This is a, whoever put this together, it's not a real month of the moon. What they did, they took the shadow, because there's no shadow, so, but the movement is very accurate, and you can see about 60% of the moon, because the nutation is what it's called, where it goes back and forth. And of course, the fact that it looks bigger and smaller is because the lunar orbit's not a circle. So it looks like it's closer sometimes than others, so it looks like that. But we'll see. I haven't read the rest of that paper. I'll see why the guy believes that it doesn't have a molten center, because I think it does. But and finally, I highlighted that guy's name again. you can use the moon and the Earth as a laboratory, basically. So in order to test the strong equivalence principle, which says that two bodies with no other forces will fall at the same speed. You know, if one's, well, Galileo, when he dropped two cannonballs, right? Well, basically, the Earth and the Moon are two very large cannonballs. It makes a very good test. And by checking the distance between the Earth and the Moon, you can verify that. And at the level we are now, it still holds up. Einstein is still right. So I put down there that different mass and composition falling at the same rate, and the question mark is, so far, yes, it holds up. However, that big station in New Mexico that has a nice big telescope, that was one of his goals. The scientists out there who built the thing is to test this even at finer levels. So he has a faster clock and a better computer and better laser, and so we'll see how he does. He's been doing it for a couple of years now. But the other thing about laser ranging, like I said, it was sort of artificial. We split it between lunar and satellite. But so far, in the last 12, 20 years, the satellite laser ranging has really taken over for several reasons. It's easier to get data off these guys because they're closer. There's some science you can do with this that you can't do with the lunar. Now, the satellites, there's several reasons for the satellites to be up there. Well, I'm talking about Geodesy, and the ones that are put up there for geodetic studies all look like they're all round balls. Some are large. This is a Geodesy put up by the Japanese about 20 years ago. It's about 9 feet across. And some of these other ones down here, these guys are only like 10 inches. But they're primarily, they're completely passive. There's nothing but solid metal and the reflectors on them. They're up there for only one reason, has to be hit with lasers. But we also track other satellites for other reasons. I'll get into the reasons why we track these guys, but it's entirely Earth studies other than gravity and position. So, do you have a question?
How long do we NASA Goddard or NASA Swift satellite on the images?
Which one's that? What images?
Is any of them the NASA Goddard or the Swift?
The Swift.
Yeah.
You talking about that? That hasn't.
Gamma ray telescope?
Yeah, we don't track that.
Oh.
Yeah, that's a different. Oh, okay.
I was wondering if any of the images were the NASA Goddard or NASA Swift satellite.
Yeah. Okay. Yeah. The question was if some of these satellites were from NASA Goddard or the Swift satellite, and we do track. One primary one we track from NASA Goddard is the IceSat. I don't know if you heard of that. That's one of the guys who's in this category. They're looking at the ice pack on the Earth. It was a big mission. I believe it's been deorbited, but just recently. I'm not sure. Yeah.
So the satellites that you described previously that are just a reflecting ball of metal.
Right.
When they're placed in orbit, but since there's no control or whatever, eventually that orbit there's no hope.
Okay.
It's going to decay.
Right. The question was about the orbits for these geodetic satellites that they're going to decay, and some of them they want them to decay. Some of these ones that were in the lower orbits, they want to watch them decay. That was part of the plan. These other ones, like this guy here on the upper left, that is Edelon. That's a Russian satellite. And that's at a 20,000 kilometer orbit. It'll be there for tens of thousands of years. So it's for studying different parts of the gravity field. Yeah.
Did they give it that particular design for like good reason, or was a big part of it to make it look cool?
Yeah, I think. I know. I sort of like this one right here. But no, actually, they have a reason. Like, for example, this one was built that way so that the lasers would hit only one cube probably, because they were getting some results off other cubes. Like this, well, that one up there especially, the cubes are almost flat to the face, so they're getting multiple returns. So that's one reason, yeah.
So that was problematic because the refused 10 meters difference.
Yeah. Oh, yeah. 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 Actually, some of the newer lasers, they can get all kinds of, they can almost take a picture of these things with a laser. They can actually, but yeah. And other things, I mean, this was done, this was used, this does have flat mirrors. These are polished metal mirrors that were used for a different experiment. And in between are the corner cubes here. But that one, this guy here, if you're up there on a clear night and we're shooting at that guy, you can actually see the reflection of your naked eye off this guy, because it's so bright. When you hit those bright flat mirrors, you can see it. I mean, with the naked eye. It's the first time I saw that, I was sort of amazed too, because that's at about when it's directly overhead, it's about 1,500 kilometers. So it's, you know, it's not close, but that's how bright lasers are too. And you can see reflections off of it.
So when we see a representation of how there are 10,000 orbiting objects around the Earth,
Yeah.
that classic picture, what percentage of orbiting objects is made up with ranging satellites? Are there a lot of them up there?
Ones that have actually corner cubes on them, probably not as many as for other purposes. I would say 50 to 100.
Okay,
You know, there's
very
not a whole lot. However, they're starting to put more missions. They're putting corner cubes on so we could hit them with a laser anyway for other reasons. You know, so no, most of the stuff in orbit is junk, and that's something else that we're getting involved in too. But let's see what we're doing. Okay, this is what I was going to talk about. The previous pictures showed you basically two. The geodetic studies are just a big round balls that won't interact with anything. There'll be less drag from the atmosphere and that kind of stuff. And those things are in orbits of 800 kilometers to about 20,000 kilometers. And I'm not sure if you've heard of any of these missions. LAGEO, Starlet, Odyssey, those are all geodetic missions. Earth sensing, the ones with all the second slide I showed you with all the panels and stuff, those are the guys that need to have their position well known so they can calibrate their altimeters. Because these guys, most of them are checking sea levels, sea temperatures and ocean circulations, ice pack. So in order for that to work, they have to know where they are very accurately in order to claim that their mainly radar altimeters are providing accurate data. The other one, of course, everyone knows GPS. The other missions, GLONASS is the Russian, Galileo is the European. In order to, they're positioning, they're determining their own position with their radio navigation. But we improve their results by tracking them. So we give them laser orbits, and they can improve their orbits from that. So it increases the accuracy of the GPS and GLONASS targets. And then there's always a couple other ones that are in there. Oh, I put this in here. Gravity Probe B was another test of Einstein's lens theory. He proposed that the Earth, while it was rotating, was dragging space and time along with it. So we actually tried. That was the very difficult one. But these experimental missions usually come and go very quickly. Yeah.
What does tethered satellite do?
Well, they were looking at how tethered satellites operate in space. It's the physics of having. Yeah, they actually. That was interesting because you could see it tumbling in Earth with our telescopes. There was two satellites. I think they were called Tom and Jerry. I think they were called, and they were tethered several kilometers apart. And eventually, they found out what would happen. There was a potential difference in an electrical current, and it broke the tether. So, but yeah, that was interesting. Now here's some of the scientific data products produced by satellite laser ranging. I mentioned the length of day. The Earth is slowing down, and this plot on the left is for the last 35 years. It's actually starting with the laser ranging period, and you see several signals in that. It's interesting. You see the yearly signals of change in mass transport caused by winter, summer. You see that going up and down. But this I have a pointer, don't I? A laser pointer. Yeah, this structure here, they don't really know what's causing it. It's got to be something deep inside the Earth, but they don't really know what's causing this kind of change. But the trend is down, so we're slowing down. And the other thing, that this polar motion, actually the pole is spinning around slightly. And this is very important for us because we even feed it back to ourselves so we can point our telescopes more accurately. So that data goes to all the observatories every day. It's updated, matter of fact. Yeah.
That length of day or that length of year measure, how far is that data going back? It's quite a variable data to draw a specific trend from.
Well, this is only the laser data.
Is this the slowing down?
This one here.
Yeah.
Yeah. This I don't really know. My life started with lasers, so this is the start of the laser ranging period. So I'm not sure if they
I'm not worried about it slowing down if that's all the data we've got.
well, yeah, it could change, but they know why it's they know why it's slowing down. The gravitational friction between the Earth, it may eventually flatten out to where it stops. Where it gets some kind of equilibrium, right? When it gets far enough away. But you don't have anything to worry about. Now, the other thing we do, I talked about, about the gravity. Another thing you do is you can actually describe or measure the gravity field by getting very accurate orbits. Sometimes you can see that blue orbit. Maybe I should do it again. I don't know if you noticed it was slowly undulating, right? Well, because it was changing as it went over points of higher or lower gravity. So you can accurately measure the satellite orbit and determine what the gravity field is. Up until recently, laser ranging was the only way of doing that. There's some new radio type missions that can do it without using lasers and do it faster actually. But
Why would gravity vary in places?
different mass in different areas, and actually it changes its dynamics. They can actually see the change from summer to winter sometimes, with the ice pack building up. And one paper I read said they could even detect it when there was a large reservoir that filled up. They could detect the change in gravity. And this actually was started at plate tectonics. I guess in the 40s or 50s, a guy named Wegener proposed that the continents aren't static, that they're moving, and he was ridiculed for it. This picture here is the last 700 million years, mainly based on geologic data, looking at the geologic data, but we can actually measure it real time. This is a recent picture, and GPS is taking off a lot of load off making these measurements because it's cheaper to put GPS sites around. But laser ranging was the first technique that actually showed in real time that Wegener was correct. And I showed you that picture of the triangle. Within the first year, they were measuring that movement, and within the next few years, everybody accepted it because the data showed, yes, things are moving around. We're moving, it says Hilo there, but we're moving about 4 centimeters per year towards Asia. And of course, it's that movement that is causing earthquakes too, and volcanoes and everything else. And I mentioned precise orbit determination before, and this to calibrate other satellites that are in orbit doing other things. And lately, measuring the Earth's climate has become more and more important. In order to get the accuracy, this is actually a picture of Jason 3. It's going to be launched soon, and it's another. It's a enhanced version of Jason 2, which was an enhanced version of Jason 1. They're getting more and more accurate. Whenever they get better electronics and better techniques, they launch. But in order to verify that this sea level is changing, it needs to know its position very accurately, actually relative to the reference frame. And we're one of the people that provide that. The laser stations around the world do that. But they also cross-check with GPS and also other techniques for locating satellites in orbit. But these are becoming more important because there's more and more of these being launched. And actually, it's almost the end of my talk now. I didn't even show any pictures of Lower Observatory. When I first put this talk together, I had about 100 slides, so I threw a whole bunch of them out. The Lower Observatory closed to make room for pan stars, And prior to that, we had stopped doing lunar ranging because NASA cut the funding and we were only doing satellite. So from my time here in 1984 until about 2004, I worked at Lure, and then in 2006, this was opened up. After they closed Lure, Maui is a very important spot. There's not many places on the Pacific Plate you can put a laser ranging site. Even on at sea level is another problem too, even though there are other places to put it. Because we're using visible light, here's our green laser, and we can't fire through clouds, stuff like that. So being on top of Haleakalā makes it a very valuable site. This is a picture taken, actually Rob took this picture, it's a very good picture. Actually NASA uses that picture in one of their brochures. That's us firing the laser towards Sagittarius. Is that Sagittarius? And then looking down, it's a very small little unit, and it's not as powerful as, let me show you the next slide, it mentions that. It's just a smaller Lure observatory. The telescope's much smaller, it's only 28 centimeters. It's actually, I have pictures of it. It's a off-the-shelf Celestron, 11-inch telescope. So the laser's not quite as powerful. Oh, there's no bathroom, I mentioned that. But it was used, it was initially, if you notice, it looks like a container. It was an old Nike site container that they converted to be a transportable laser station. And during the 80s and 80s to mid-90s, it was moved all over the world and put in places for 3 to 6 months. It had been Canada, Central America, South America, then Europe. This will probably be its last site. It's more or less permanently here until something else better comes along. I think I already mentioned that the reason we moved it. And actually it's been, there's about 33 laser observatories around, and TLRS-4 is the name of the observatory, Transportable Laser Ranging Station is the NASA name for it. This is the highest altitude that's ever been deployed. And we showed some of their models to be wrong. With the small telescope, they thought we couldn't track some of the higher satellites. But we did, mainly because, like I said, the models were wrong. Because being at 10,000 feet, you're above 70% of the, or 30% of the atmosphere. It made a big difference for us to track. So we were able to actually track GLONASS, which is a 20,000 kilometer orbit, and they had never been able to do that anywhere else. We are funded full-time by NASA. We operate 7 days a week, 10 hours a day, and we work day and night. And I already mentioned this will probably be the last deployment of TLRS-4 because there's other things coming up. In the future, when I first started here, there was only like 12 observatories around the world. Most of them were NASA observatories, about half of them. Now there's over 33 that are operating constantly, and there's probably over 40 that are actually working from time to time, owned by, run by 28 different countries. So it's become a really international scientific experiment. The biggest thing, of course, is the measurement accuracy has gone from 1/10 of a meter to 1/1000th of a meter. And we're right now approaching sub-millimeter accuracy. In 1998, everybody got together and formed the International Laser Ranging Service. Before that, all the countries were sort of operating on their own. And this brought everybody together into one service. It had common standards, common goals and stuff. And one other thing in the future why I say we won't be around much more, not in our present format, is they're deciding to use core sites in what they call the Global Geodetic Observing System. They want to do is have certain sites around the world that have all the techniques that are used for geodesy in one site. And they would probably only be 15 or 20 max that would be needed to do the science we need to do. And luckily they need one in Hawaii, so there's certain to be one on Haleakalā, at least part of it in Haleakalā. This is the International Laser Ranging Service members right now. Like I said, some of these are directly run by NASA or funded by NASA. Others are actually partially, like in South Africa, Hartbeespoort. NASA provides the equipment and a university down there runs it, sort of like we do here, and same with Tahiti. But most of these are run by individual countries all cooperating through the International Laser Ranging Service. I think right now the Russians have the largest number of satellite stations right now. Oh, to end the talk, I want to show what it looks like when this is a brief video I took a few years ago using a light amplification goggle, which uses the same technology, MCP technology, to amplify the light. But you can see the laser's firing 5 times a second, and once it fires, we actually have to see a return before we fire the next shot. So that tells you how fast things are moving. And finally, this I put this together for open house. We have a surveillance camera, low light camera outside, looks at the dome. I put a small camera inside to look at the Celestron telescope. This is, like I said, this is only 11 inches at the back of it, 11-inch telescope. And the operators, in order to actually see if we're actually hitting anything, have to look at an oscilloscope, which is a device that will display electrical signals, right? So this thing's hooked up, gets some of the signal from the MCP, the detector, and the only way that the operator knows that they're actually getting returns is if they see a spike in here where they get a signal. So let's see if this will work. So this is 20 times, sped up 20 times, so it's not real time. But you can see our green laser sort of overwhelming the camera right there. And I'm not sure, like I said, it was a frame was taken every 20 seconds. So I'm not sure if this guy got any data on this one or not. But I think the next one shows what it looks like when they get data. And it looks like a beam, but it's not really a beam. When you're there, you actually see the flashing, the 5 hertz flashing. And you'll notice some of these, even when it's one frame in 20, some of these move very quickly. Some of the low satellites that are 400 kilometers, they're above us for a minute and a half. They're just flying. So this one's, let's see if it gets any data. Come on. Yay, there you go. So when they see that, they know they got data. It's like a video game. They have a setup with GUIs, and they have a mouse, and they move the mouse around. It puts little biases in the telescope trying to find it. But lately, the predictions are so good. Most of the times, you get a return on the first shot. You just fire and you get it.
Is there a flash in that same frame? It looked like they were shooting.
Who's that? I saw something else?
Yeah, right behind the Air Force is concerned.
Oh, I didn't see that. It could have been. But this is one of the fast guys. You can tell the signal's stronger too. It's closer, right? So it got a bigger. That thing's proportional to the signal, return signal. But I'm sorry. Well, the question was there another laser in the background? And I didn't notice it. It's possible, but the Air Force does have lasers too, and from time to time you'll see them. But we do completely different work from the Air Force. That's another thing I should point out. The data we get here, these range measurements, if you wanted to, you could get on the NASA's website and download them yourself. And so it's open to anybody. So again, they're not getting any data. And you can, once in a while, you can see the light there. If it catches at the right frame, you can see the laser light coming out of the. How? Yeah. But,
Your first question.
yeah.
These lasers are all non-destructive, right?
No.
They are destructive.
Well, they can be if these lasers are non-destructive. All lasers probably could be destructive. It depends on how much damage they can do, right? This guy here, if you put your hand in front of it, you might feel a little warm, but if it hits you in the eye, it blinds you instantly, because it's each pulse is the average wattage is only half a watt for that thing, but because the pulse is so short, the peak power is over 1 billion watts. So and I've seen this laser we have here. It's a small little laser. The laser techs, when they were tuning it once, showed me, they blew a hole through a quarter with one pulse. So if you focus it, you can. But we don't focus it. We noticed when it comes out the dome, it's fairly large. So like I said, you can put your hand in it, it wouldn't hurt. But you can't put your face in it. And it's also, we actually hire people to make sure we don't hit airplanes. So we have people out there to make sure we don't point towards airplanes. So who had next?
This international organization that started in '98 so that everybody's communicating about the satellites.
Yeah.
Is that body aware of all, like you said, did you say that there were thousands of satellites up there?
Well, the ones that are being tracked by the International Laser Ranging Service is probably right now, oh, I'm sorry. Okay, the question is how many of the total satellites in orbit are being tracked by the members of the International Laser Ranging Service. It's a small subset because they usually have missions 1 or 2 or 3 years that everybody focuses on those, and then we go to the next mission.
So are there's satellites that other countries don't know what the purpose of them are?
Oh, I'm sure there are, yeah. Yeah. Matter of fact, we have to get permission to, well, the question was the countries don't know what other satellites do, and that's, that's part of what countries do. And we can't fire at a satellite unless we get permission. It would be bad. Yeah. Let me try to get back here.
For the satellites, the ones that you showed earlier, the type of satellites they have up for specifically shooting laser tags.
Yeah.
Is this a standard protocol to let other people know you're shooting at it so they don't do it at the same time?
Well, actually, the question was on those satellites that are up there high. Do we only one station fire at them at a time? And the answer is no. Everybody, some of those high satellites, you'll have 5, 6, 7 laser stations firing at all at the same time. So, yeah.
So does that mean that somebody managed to get their hands on a laser that was large enough, and they managed to be able to focus at it, that they would be allowed to fire at it without having to check with everybody?
No. No, the question was, do you need, that goes back to about permission. He was asking, do you need, could you fire at these without permission? And no, you could, but if they discovered it, they would probably come after you. So, let me try it back here again.
The index of refraction of the atmosphere is greater than 1.
Yeah.
So is that factored into these really precise measurements?
Oh, yeah.
Going through atmospheric, conditions as well as in the vacuum of space, which is 1.
Okay, the question was about the atmosphere and how it impacts the measurement.
Yeah.
And is that refraction, the atmosphere is the biggest uncertainty. They spent many years modeling it, and we include that model when you do the range measurement. You subtract the error caused by the atmosphere, and that's been fairly. It's still, and off the top of my head, I can't tell you what kind of error it introduces, but it's been so thoroughly studied by, specifically by lasers. They'll do special studies firing 2 different colors to find out what the difference, directly determine what the refraction is. So you get very precise corrections. But yeah, that is a big error. Okay.
When would you want to use radio waves? When would you want to use lasers to do geodesy?
Well, okay, the question was, when would you use radio waves to make measurements versus light? Well, the difference is radio waves have a wavelength of meters, so the accuracy would be in the meter range. The laser light has a wavelength of nanometers, so or you get my point. It's much more accurate to use a much greater wavelength. Okay.
Were you guys ever shut down by snow for the night or something? Like the latest snows?
Were we ever shut down by snow? Yeah, right there we were. This was a couple of years ago. Yeah, the lasers are very sensitive to weather, so we can't fire through clouds or rain or fog or snow. So, one more? Okay.
How much of a problem does the ionosphere play?
Oh, for us, none. Yep. Because we're not radio, we don't interact with the ionosphere. That's there are radio waves, of course, react with the ionosphere. So GPS has to worry about the ionosphere, but we don't. Good question. Yeah.
One of the things you had a triangle with a satellite and then the distance of two stations on Earth.
Yeah.
How do you know the distance between those two stations when the Earth is curved and you can't see each other? How do you know?
Well,
How can you calculate?
those are points.
I know, right?
Right, they're points. So they're just. Oh, I'm sorry. How can we be sure what when you make a measurement using?
California to Maui.
Yeah. How can we be sure that those the distance is correct? Well, it's not measuring the curve; it's just measuring the relative motion between them. So, it's again, I'm not an analyst. You know, I get the data. I do read the papers, but yeah, yeah, they're looking at this relative movement between these guys. So they're not trying to measure the curve distance. It's just the direct distance between them.
So I thought you were saying something about going up the angle. Once you know the angle, and then you know the distance between them.
Yeah.
You could do certain things. Well, how do you know that distance between them exactly?
Well, geometry, I guess, just because you have triangles, right? You can figure out what the missing leg is and stuff from knowing what the other sides of the triangle are. So, yeah.
Two questions. Am I correct? You're putting the laser into the eyepiece end of the telescope?
I don't have the picture. It goes in the. There's a it's a slightly modified. You know, there's where the eyepiece is. We do have a turning mirror there, so it comes in the side.
So the laser is being spread out as it leaves the telescope.
Yeah, the Celestron has a secondary mirror. So his secondary mirror hits the primary and then goes out.
So you're not maintaining the tightest laser beam width.
No. Yeah.
Okay.
Yeah.
Okay. The other question is, so you've explained that sometimes you're only getting single photons on a return.
Yes, you can.
Okay. So at that point, as the single photon enters the optics of the telescope, I would imagine that there's a quantum effect in the refraction, because now it's the particle is interference, the wave particle duality, there's an interference from a single photon.
Yeah. Yeah.
How does that play out?
Well, do you understand quantum mechanics? Well, the question was, is there any quantum mechanical interference from photons coming through the telescope? And there is, but remember, light is a wave and a particle, right? So you have that, you know.
How is that accommodated in the measurement when you're down at the level of a single photon that's interfering with itself?
Well, if it interferes with itself, you may not see it, right? And you talk about, yeah, I guess I'm not really understanding the question. I have not looked at this. The question is, how do we handle the quantum mechanical effects? And there obviously, I don't know for sure, but there aren't any that are causing us not to get returns, whatever it is. So it works, but I can't tell you. I couldn't tell you at that level why.
So the measurements and process is above the level that would be impacted by lower levels.
Yeah.
Events.
Yeah. Right. So you have another question, Jenny?
Following up on the single photon question, you mentioned the signal to noise problem. How do you, in that case, if the signal is a single photon, how do you know that's your photon?
Yeah, that's some of the scientists used to call the ones that are in there volunteers. But it's done statistically. You can actually use statistics look at a whole bunch of what looks like noise, and actually sometimes you can actually see it if you plot it. You'll see if you plot all the returns on a 2D plot, you'll see all these little dots all over the place, and you'll see one little area, one little line that has more dots than the other ones. So statistically, you can pull that out. It is with our system, of course. You saw how big our returns are. We're not dealing at the one photon level anymore for the satellites. We know we got returns, but a lot of the lunar people still have to do statistics on their data.
So it would seem that if you had technicians there, that just the presence of a technician or engineer would collapse the wave function.
The question was another question about the wave function collapsing, and I'm not prepared to answer that. If they do, well, I can tell you for sure that they don't, because we do have people there and it doesn't collapse. So. The biggest one we fire at, the one from Apollo 15, is about a meter square. It has quite a few reflectors. That's the one that always gave the best. Oh, the question was the size of the reflectors on the moon. And Apollo 15 had the largest. And the other two were about half that size. One was from Apollo 11 and 14. And yeah, I forgot how many actual corner cubes are on there. But you could tell the difference when we were tracking. You'd see them. It was easier to get returns off Apollo 15 than any other one. Okay, what?
Two questions. One boring, one more boring. The more boring one is you weren't going to talk about reference measuring on the Earth or something like that. Just give a minute or so on what that is. That about giving really accurate positions?
Well, yeah. In order to make measurements, you need reference points. And one of the things that we produce is the International Terrestrial Reference Frame. So it's a frame that's updated every few years when we get more measurements that sort of like latitude, longitude, and height, but it's more precise than that. And it follows the geoid, the gravity fields and stuff. It's much more precise than that. So
does that give fixed points, like trig points where you can do a reference from?
yeah. If you have the reference frame, that's what you use to make your calculations. You use the reference frames to make your calculations. So.
Second question, which is also boring, but maybe not.
Well, I like mathematics when I'm working.
This one's more amenable. You say you're up there 10 hours at a stretch and there's no bathroom. How do you
Well, the question was, how do the guys stay up there 10 hours without a bathroom? Well, that actually came up when they negotiated, when NASA was negotiating the contract, because they want, there's bathrooms next to Mee's Observatory. This picture was taken from close to Mee's Observatory, so there's bathrooms there. So you have to leave the site to use the bathroom. But
Is the moon the upper limit of the laser?
Yeah. For the lasers we have, that's the limit. But it actually to get meaningful returns. But what they're doing now, matter of fact, the lunar orbiter had a laser on it to fire back. So they're using transponders. So you throw a laser out there, it sees it, and it fires a laser back at you. So you can go. They actually got returns from one of the Mars orbiters on its way to Mars, and that's a good story too. One of the scientists, the things have 3/4 to Mars, and he said, you know what, we can turn that thing around and test the transponder, and they did. They turned the aircraft, the spacecraft around, and they fired a laser from Earth, and it fired back. They saw it. It was I thought it was amazing.
How long did that take to get back?
Boy. Minutes, 8 and 10 minutes, something like that. Yeah. Daryl?
I had a question. You were just talking about that. I think I read something about that lunar transponder. Weren't they sending actual internet traffic on that? They were actually.
Well, that's a separate experiment. They actually sent a picture of Mona Lisa. I'm sorry. I was supposed to repeat the question. Yeah, are they actually doing internet traffic between the moon and the Earth with lasers? And the answer is yes. That's probably what's going to happen to all communications. They're going to be going over to lasers because it's much higher bandwidth. You can send much more data. So they're going towards that. Yeah.
Okay, so not for your particular site, but if you acquire different color lasers and objects, I don't know, maybe this is just my lack of understanding of waves, but when you have the different colors of lasers and you have the different wavelengths, does that affect your return time at all, or does that affect either atmospheric refraction? Do you take those things into account?
Well, the question was, do different color lasers have different transit times? And the answer is yes. Through the atmosphere, they do. So if you're in a vacuum, no. And I think I mentioned two-color arranging. You can actually use the difference in return time to get a direct measurement of the refraction in the atmosphere, because it does take different times for light to go through atmospheres of different colors. I'm sorry. Okay. Okay, there's going to be